Greetings everyone, we are the SEG2 and we are here to present our research project titled Thermoplastic Fiber Reinforced Engineered Geopolymer Composite or EGC infused with powdered waste glass as partial replacement to cement. Concrete, although considered as one of the most consumed substances, is prone to cracking due to its poor durability. On the other hand, ECC is a class of high-performance fiber-reinforced cementitious composite which is designed to achieve high tensile ductility and incorporated with randomly short polymer fibers. Moreover, it shows excellent crack control and pseudo-ductile behavior up to tensile strain of 3 to 5%. As shown in figures 1.1 and 1.2, ECC exhibits excellent compressive strength and flexural strength compared to conventional concrete. However, one of the disadvantages of ECC is its mixing design where coarse particles are frequently omitted, resulting to a higher cement concentration than ordinary concrete. High cement concentration increases the shrinkage, hydration heat, and expenses, and also negatively impacts the environment. Having said this, production of EGC is a viable solution to these problems. Engineered geopolymer composite is a new technique that blends geopolymer and ECC in a single material. It is a more environmentally concrete since it replaces the cement binder in ECC mix design with an alternative cement-free binder like geopolymer.
With that, this experimental study relies heavily on utilization of waste materials such as waste glass and surgical face masks and how they can be complemented in creating a sustainable construction material like EGC. Glass is an inorganic solid material that is usually transparent or translucent. Due to its chemical composition and physical properties, glass is a recyclable material that has been strategically recycled in the building sector. On the other hand, surgical masks have become abundant as a result of the COVID-19 pandemic, which poses an environmental issue. Thus, material component of surgical mask composed of three layers of thermoplastic fibers, with which these fibers, polypropylene and polyester, are commonly used as fiber reinforcement in ECC.
So, what are the problems our study aims to solve? Although concrete has been used for decades, it could still be subjected to improvement, since conventional concrete is practically unbending, brittle, and inflexible with a strain capacity of barely 0.1%. Aside from that, as shown in the figure, building construction and operation accounted for 39% energy-related CO2 emissions in 2018. This includes the manufacturing of materials like cement. Hence, production of cement can be reduced as well as being energy efficient by recycling glass from landfills that impose land pollution. Another problem which is relevant today and has a long way to go is the disposal of millions of face masks. This waste is categorized as infectious waste that risks the health of not only humans but also marine animals.
With that, this research aims to develop a sustainable and innovative concrete by utilizing extracted thermoplastic polymers in surgical face masks as fiber reinforcement and powdered waste glass as partial replacement to cement. Specifically, this aims to maximize the strength enhancement effect of waste glass and thermoplastic fibers from surgical face masks to ECC by determining the optimum percentage. Develop a quality, sustainable, and resilient design of concrete by integrating an eco-friendly approach in ECC to make an EGC, and investigate the reaction performance of incorporating thermoplastic fiber and waste glass to the physical and the mechanical properties of EGC.
Moving on, the study aims to contribute in construction industry development while providing long-term help in the United Nations SDG goals number 11, 12, and 13. The study will help in climate action by producing energy-efficient material EGC. EGC, a bendable concrete, could build greater quality infrastructure that will last longer than buildings made out of conventional concrete, leading to sustainable cities and communities. EGC is incorporated with recycled materials, waste glass powder, and surgical face mask fiber, which aids responsible consumption and production.
Several studies supported the feasibility of this project. According to Jacek et al. 2014, Engineered cementitious composite is a form of high-performance fiber-reinforced cementitious composite, a new concrete material with great potential for enhancing concrete construction durability. However, despite promising characteristics of ECC, Ku et al. 2018 highlights that mixture design of ECC imposes a negative impact to the material itself and to the environment due to its higher cement concentration. Therefore, it is suggested that replacement of a portion of cement in ECC is required to provide a practical solution to these concerns, like in engineered geopolymer composite. In the production of EGC, incorporation of industrial waste or byproducts as a supplementary cementitious component of cement is vital. Waste glass is an ideal pozzolanic material containing a significant amount of silica. Based on the study of Sadukul et al. 2017, highest compressive strength and flexural strength is achieved at 20% optimum replacement of waste glass powder to cement. Moreover, ECCs are often reinforced with short fibers and micromechanically designed to have high tensile ductility and repeated cracking according to Kin et al. 2020. Martin Lynch 2021 suggested that utilizing face mask as reinforcement in concrete shows substantial upgrades in the mechanical property and workability of the concrete with the help of a superplasticizer.
In the theory presented by Leonhardt 1988, concrete cracks initially occur during and after concrete hardening. Naose et al. 2007 stated some of the parameters that affect these cracks to form, and these are the cement-water ratio, the air content, the curing time, fine aggregate content, gravel content, grade, and kind to consider. Uzair Ali and Zakir 2019 noted that a concrete has high compressive strength but low in tensile strength, resulting in the emergence of countless microcracks. In addition, Mindset 2008 started that the failure of the properties of concrete are influenced by the condition of the stress. To solve these challenges, a type of extremely ductile concrete, commonly known as bendable concrete, was developed in the last decade. In the Journal of Satish Kumar in 2016, stated that the ECC behaves more like a ductile material or metal than a brittle glass. Many of the ductility properties faced by concrete can be overcome by adapting ECCs. Moreover, they explain that the interaction between the fibers and the cementing matrix is largely responsible for these distinguishing ECC features.
The concept of the studies originated from the bendable concrete. Bendable concrete has the same components as conventional concrete, but with reduced coarse aggregates, and it's reinforced with polymer fibers. Cement, sand, water, fiber, and admixtures are the main components in creating a technical ECC. However, since these components are all non-renewable, this study aims to lower the energy consumption by partially replacing ordinary Portland cement with powdered waste glass and maximizing the main composition of surgical face mask by extracting its polypropylene and polyester fibers and using it as fiber reinforcement in the study.
Fabrication procedure of the project is shown in the flowchart. The process will start from the collection of materials. Then when the materials are all ready, concrete mixtures will be formulated and will undergo slump test. 126 specimens will be made and will be subjected to compressive and flexural strength tests after the curing period. The waste glass bottles will be collected and cleaned before being cut and ground. Then it will be sieved and shall pass through sieve number 200 and will partially replace cement by 20%. As for the thermoplastic fibers, unused surgical face masks and commercially available thermoplastic fibers will be gathered. Surgical mask fibers will be manually extracted and the latter will be trimmed to a length of 12 millimeters. Then, these fibers will be coated with an anti-friction coating.
The design mixture to be used in this project is a Class A concrete with cement to aggregate ratio of 1:2:4, which is theoretically have a compressive strength of 3,500 psi. There will be 7 mixtures and 2 varieties. The variation of mixtures will be used to determine the material property of fibers from surgical face masks by comparing the performance of the two sets of mixtures, whereas set A will contain extracted fibers from face mask, while set B will contain store-bought fibers. All the specimens will contain a water-cement ratio of 0.4 to attain the aimed strength and durability.
After creating the concrete mixture as per ASTM C192 to test the workability of fresh concrete, concrete mixture will undergo slump flow test in accordance to ASTM C143. Then using a shovel, the concrete mixture will be poured in 6 by 12 inch cylindrical molds and 4 by 4 by 12 beam molds to be subjected to compressive and flexural strength tests as per ASTM C31.
The study will be performed from March to July. Following are the major activities and its corresponding estimated time. Gathering of materials will be in the first 2 weeks of March, while feeding and processing of materials will be within the last 2 weeks of March. Preparation of specimen will be done in the first week of April. Curing period will be from the last 3 weeks of April up to the first week of May. Testing of specimen will be done every 7, 14, 28 days of curing from the last 2 weeks of April up to the first 2 weeks of May. And lastly, evaluation of results will be from the last 2 weeks of April onwards. This study is expected to take 5 months to complete, and here are the list of references we acquired in preparing the PowerPoint presentation. And that would be all. Thank you.